Hello everyone, welcome to this lesson. So in this lesson we're going to go through the second method for finding roots of equation and the second of the bracketing methods, which is the false position method. Now if you remember from the previous lesson, we covered the bisection method, which actually gets the root by taking an average of the upper and lower limit. But also, if you've noticed, this is kind of a brute force technique where it only takes into account the x values of the upper and lower limit. What's different with the false position is the false position actually takes into account the function value of the upper and lower limit. Because the idea is, for example, if the function value at the lower limit is less than the function value at the upper limit, it's logical that the root should be closer to the lower limit than it is of the upper limit. So this is what the false position method takes advantage of. So how does the false position method work, or how is it even derived? So what we're going to do is, if you look at the first application here, the graph here, we're going to take a line and we're going to connect the function value at the lower limit with the function value at the upper limit. And the intercept of this line becomes the estimation of the root. Now let's actually derive the false position method and create an equation for XR. So how do we do that? If you notice with these two triangles, they're similar triangles in which the slope is the same. And we're going to use this fact to actually create an equation for XR. So the slope for this triangle here is basically the rise, which in this case is the function as at XL, and also the run, which is XR minus XL. So this is going to be the slope of the first triangle here. Now is going to be equal to the slope of the second one here, and the rise here is the function at XU divided by the run XR minus XU. And if we rewrite this equation, we're going to get this expression here for XR. So let's actually go through and explain the false position a little bit more and going through three applications as we did with the bisection. So if you looked at the first application here, I'm going to use an upper limit of 2.5 and a lower limit of 1. And you're going to see when we connect these two, we're going to get an XR here. And if we use this equation to figure out what that XR is, we're going to find out that the first estimation is 1.8 at a true error of 10%. Now, if you remember with the bisection, the first one had a true error of 12.5%. So even from the first application, we have definitely an improvement. So if you look at the second application, here the root is on the right interval. So basically we're going to be dealing with the interval of 1.8 and 2.5. So if we do the same thing, so this is kind of a visualization of the false position. And to get this root, we're going to use this equation still. So we're going to be applying the lower limit of 1.8 and the upper limit of 2.5 with their corresponding function values. And that's going to give us a root of 1.9697. With a true value or a true error of 1.515%. So very, very good improvement over the first application. And if we compare it to the second application of the bisection at 6.25, definitely a massive improvement. Now, if you see, we still have the roots housed on the interval on the right. So we're going to be taking basically the interval of 1.9697 and 2.5. So we're going to take this upper and lower limit with their corresponding function values. And we're going to be using, of course, the false position. And this is going to give us 1.9956. As you can see, this is the visualization of the false position, and you can see we're extremely close. That intercept between the line connecting the function value of the upper limit and lower limit is almost grazing the two at 1.9956, and that gives us a true error of 0.218%. Now, if we compare this to the third application of the bisection at 3.125%, we can see it's a massive improvement. So actually taking into account the function values at the upper and lower limit created a massive improvement to finding roots of equations. So to kind of recap, so here the false position takes into account the function value, the upper limit and the lower limit, and it uses the concept of similar triangles to create this equation here by taking the fact that the two slopes are equal. So we have created the slope for the triangle on the left equal to the slope for the triangle on the right. We have rewrote it into this expression, which is the false position method. So this is how so it's a very simple derivation. We have seen from the first application we got an approximation with a 10% error as compared to 12.5 for the bisection. So from the first application is definitely outperforming the bisection. The second application, 1.515%, still superior, and also with the third it turned out to be 0.218%. So it's a very, very simple technique. It's a very powerful technique, and you can see that it converges in just 3 applications to an estimation that is very, very, very accurate. Now in the next lesson, we're going to be creating the Python code for the false position method, and we're going to go with testing different error criteria, 0.1, 0.01%, 0.001% estimates. And also you're going to see that actually the false position method code is really only 1 line of code difference from the bisection method. So that's it for this lesson, and I will see you in the next lesson.